Tonight we are going to talk about one of the most dramatic reversals in the history of science. Not a small correction, not a refinement of existing ideas, but a fundamental overturning of things that some of the most brilliant minds in human history believed with confidence. Things that were written in textbooks, taught in universities, accepted as settled, and then discovered to be wrong in ways that nobody anticipated. Black holes. For most of the time that scientists have thought about black holes, they have thought about them incorrectly. Not wildly incorrectly, not in ways that made no sense, but incorrectly in ways that turned out to matter enormously. The corrections required new mathematics, new physics, new ways of thinking about space and time and information and the nature of reality itself. Some of those corrections are still being worked out. What we thought we knew about black holes was wrong. What we have learned in their place is stranger, more beautiful, more disturbing, and more profound than what it replaced. This is Science for Sleep, and tonight we are going to move slowly and carefully through what we got wrong, why we got it wrong, and what the truth appears to be instead. Settle in. Let the body find its ease. And let us begin with what a black hole was supposed to be. The concept of a black hole has a longer history than most people realise. In 1783, a British clergyman and amateur scientist named John Michell published a paper in which he speculated about what he called dark stars. Michell reasoned, using Newton's theory of gravity, that if a star were massive enough and compact enough, the escape velocity from its surface would exceed the speed of light. Light, he reasoned, would be unable to escape, and the star would be invisible, a dark star. This was a remarkable piece of reasoning for its time, but it was based on a Newtonian picture of gravity that turned out to be incomplete. Newtonian gravity treats gravity as a force between masses acting across space. It treats light as particles that can be slowed by gravity. In Michell's picture, light fired upward from the surface of a very massive compact star would be slowed, stopped, and pulled back, the way a ball thrown upward is eventually pulled back by gravity if its speed does not exceed escape velocity. This picture is not quite right. Light does not behave exactly like a Newtonian particle. But the intuition that sufficiently compact massive objects might trap light was correct, and Michell deserves credit for seeing it. The modern concept of a black hole emerged from Einstein's theory of general relativity, published in 1915. Einstein did not initially predict black holes himself. He found the equations of general relativity so complex that he assumed they would only be solvable in idealized special cases. Within months of the publication of General Relativity, the German physicist Karl Schwarzschild, writing from the trenches of the First World War, found an exact solution to Einstein's equations for the gravitational field around a perfectly spherical, non-rotating mass. Schwarzschild's solution contained something strange. At a specific radius from the centre of the mass, now called the Schwarzschild radius, the equations produced a singularity, a point where certain quantities became infinite. For the Sun, the Schwarzschild radius is about 3 kilometres. For the Earth, it is about 9 millimetres. For any real astronomical object, the Schwarzschild radius is far smaller than the object itself, buried inside it, which is why ordinary stars and planets are not black holes. But the mathematical singularity at the Schwarzschild radius troubled physicists. What did it mean? Was it a real physical feature of space, or was it a mathematical artifact of the coordinate system Schwarzschild had used? For decades, this question was debated without resolution. For most of the early 20th century, the mainstream view was that black holes, in the sense of astronomical objects compressed within their Schwarzschild radius, almost certainly did not exist in nature. Einstein himself doubted their existence. The idea that nature would allow matter to be compressed to such extremes seemed unreasonable. That view turned out to be wrong. The first and most basic thing we got wrong about black holes was that we thought they were probably theoretical constructs that did not actually occur in nature. This skepticism had a reasonable basis. The equations of general relativity allow for black holes mathematically, but whether matter can actually be compressed into a black hole depends on the physical properties of matter under extreme conditions. If there is some physical process that halts the collapse of matter before it crosses its Schwarzschild radius, then black holes do not form, and the mathematical solutions describing them are interesting, but physically irrelevant. For a long time there were reasons to believe such a halting process existed. Ordinary stars are held up against gravitational collapse by the pressure of hot gas, produced by nuclear fusion in the stellar core. When a star runs out of nuclear fuel, the core begins to collapse. For stars of sufficiently low mass, this collapse is halted by a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being compressed into the same quantum state. The result is a white dwarf, a compact stellar remnant roughly the size of the Earth but with a mass comparable to the Sun. For somewhat more massive stars, even electron degeneracy pressure is not sufficient to halt the collapse. The electrons are forced to combine with protons to form neutrons, and the collapse is halted by neutron degeneracy pressure, a similar quantum mechanical resistance but among neutrons. The result is a neutron star. An extraordinarily dense object, typically only about 20 kilometers in diameter, but with a mass 1 to 3 times that of the Sun. The question was, is there an equivalent process that halts collapse for even more massive stars? Is there some form of matter that becomes rigid under extreme compression, providing a pressure that prevents the formation of a black hole? In 1939, the physicist J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder published a paper that answered this question definitively and uncomfortably. They showed, using the equations of general relativity, that for a sufficiently massive star that has exhausted its nuclear fuel, there is no known physical process that can halt the gravitational collapse. The star collapses continuously, compressing through the Schwarzschild radius, forming what we now call a black hole. This result was not immediately accepted. Einstein, reading Oppenheimer and Snyder's paper, remained skeptical that such objects could actually form in nature. The paper was published on September 1st, 1939, the day Germany invaded Poland and the Second World War began. It attracted less attention than it might otherwise have. For another 2 decades, the physics community remained divided on whether black holes actually existed. Then, in the 1950s and 1960s, a new generation of physicists, including John Archibald Wheeler, who coined the term black hole, Roger Penrose, and Stephen Hawking, developed the mathematical tools needed to analyse black holes rigorously, and the picture changed dramatically. Penrose proved in 1965 that the formation of a singularity inside a collapsing star is not an artifact of special symmetry assumptions. Any sufficiently massive collapsing object will inevitably form a singularity. This theorem made the existence of black holes in nature essentially certain, given what we know about the mass ranges of dying stars. And then the astronomical observations began to confirm what the mathematics had already told us. In the 1960s and 1970s, astronomers discovered quasars, extraordinarily luminous objects at the cores of distant galaxies, and X-ray binaries, stellar systems emitting intense X-ray radiation that could only be explained by matter falling into extremely compact objects. The objects driving these phenomena had masses far too large to be neutron stars. They were black holes. The first thing we got wrong about black holes was not believing they existed. Once black holes were accepted as real, the next layer of misunderstanding concerned the nature of the event horizon, the boundary that defines the black hole. In the popular imagination, and in the early scientific picture, the event horizon was conceived as a dramatic boundary, a surface at which something catastrophic happens to anything that crosses it. The popular intuition was that an object falling into a black hole would be torn apart at the event horizon, or would experience some dramatic transition as it crossed from the outside universe into the black hole. This intuition is wrong. The event horizon is not a physical surface. There is no membrane there, no barrier, no region of particularly intense gravity at that location. For a sufficiently large black hole, an observer falling through the event horizon would notice nothing special at the moment of crossing. The local environment at the event horizon is, in principle, indistinguishable from any other region of space. This seems counterintuitive. How can the most important boundary in the universe, the point of no return, feel like nothing special? The answer lies in the global nature of the event horizon. The event horizon is not defined by local conditions, but by the global causal structure of spacetime. It is the boundary beyond which no causal signal can escape to the outside universe. But this is a property that depends on what happens far in the future, not on what is happening locally at the moment of crossing. An observer falling into a large black hole crosses the event horizon without knowing it. There is no marker, no sign, no physical sensation that says you have just crossed the point of no return. The realization only comes later, when the observer attempts to send a signal outward and finds that it cannot escape, or when the observer begins to detect the increasing gravitational gradient as they approach the singularity. For a small black hole, the situation is different. Smaller black holes have more curved spacetime at their event horizons, and the tidal forces, the difference in gravitational pull between different parts of an infalling body, becomes significant before the horizon is reached. For a black hole of stellar mass, a few times the mass of the Sun, the tidal forces at the event horizon would already be strong enough to tear a human body apart, a process astronomers call spaghettification. For a supermassive black hole of millions or billions of solar masses, the tidal forces at the event horizon are actually quite mild, and an observer could cross it without immediately being destroyed. But in either case, the crossing of the event horizon is not the locally dramatic event the popular picture suggested. It is a global boundary, not a local one. The drama of the event horizon is not in what happens at that moment to the infalling observer, but in what it means for the future of that observer and their relationship to the outside universe. This shift from the event horizon as a physical barrier to the event horizon as a global causal boundary was an important correction to the early picture. For a long time, one of the central beliefs about black holes was captured in a phrase coined by John Wheeler: black holes have no hair. The no-hair theorem, developed in the 1960s and 1970s, states that a black hole in equilibrium is completely characterized by only three quantities: its mass, its electric charge, and its angular momentum, its spin. Nothing else. No matter what kind of matter fell into the black hole to form it, whether it was made of hydrogen or iron or neutron star material or light or antimatter, the resulting black hole retains no information about the composition or detailed structure of the infalling matter, only mass, charge, and spin. This was a beautiful and elegant result. Black holes, despite being the products of enormously complex astrophysical processes, were predicted to be the simplest macroscopic objects in the universe. 3 numbers, and you know everything there is to know about a black hole. The elegance is real. But the no-hair theorem turned out to be the seed of one of the most profound crises in modern physics. If black holes retain no information about what fell into them, then information is destroyed inside black holes. A book falls into a black hole. A nuclear bomb falls into a black hole. A person falls into a black hole. In every case, the detailed information about the structure and composition of the infalling object is lost. The black hole that results is identical in terms of mass, charge, and spin regardless of whether it formed from a book, a bomb, or a person. This seems philosophically uncomfortable, but perhaps physically acceptable. Until Stephen Hawking pointed out that it is not just philosophically uncomfortable, it violates one of the most fundamental principles of quantum mechanics. Quantum mechanics is, at its foundation, an information-preserving theory. The evolution of quantum states is governed by the Schrödinger equation, which is time reversible and information preserving. If you know the complete quantum state of a system at one moment, you can in principle reconstruct the quantum state at any other moment, past or future. Information is never destroyed in quantum mechanics. But if black holes destroy information, then the combination of quantum mechanics and general relativity leads to a contradiction. Either quantum mechanics must be modified to allow information destruction, or general relativity must be modified to prevent it. Or something else is going on that neither theory correctly describes. This is the black hole information paradox. Hawking identified it in the 1970s. It has not been resolved. It is one of the central open problems in theoretical physics, and it emerged from what appeared to be the elegance and simplicity of the no-hair theorem. Black holes are simple, and that simplicity turns out to be a profound problem. In 1974, Stephen Hawking made a discovery that shocked the physics community and changed our understanding of black holes permanently. Black holes are not cold and dark. They radiate. This is known as Hawking radiation, and it follows from the intersection of quantum mechanics and general relativity in a way that was completely unexpected. The argument goes like this. In quantum mechanics, the vacuum of space is not truly empty. It seethes with quantum fluctuations, virtual pairs of particles and antiparticles that flicker in and out of existence on timescales so short they cannot be directly observed. Normally, these virtual pairs annihilate each other immediately. They exist for a moment, and then they are gone. Their energy borrowed from the vacuum and returns so quickly that they leave no lasting effect. At the event horizon of a black hole, something different can happen. A virtual pair can form right at the horizon, with one particle inside the horizon and one outside. The particle inside the horizon cannot return to annihilate with its partner, because nothing inside the horizon can escape. The particle outside the horizon, finding its partner gone, has no partner to annihilate with. It becomes a real particle, carrying real energy, and it can escape to infinity as radiation. The energy for this process comes from the black hole itself. Each particle that escapes carries away a tiny amount of energy, which means the black hole loses a tiny amount of mass. Slowly, over an extraordinarily long period, the black hole radiates away its mass and eventually evaporates completely. For a black hole of stellar mass, the Hawking temperature is extraordinarily low, far colder than the cosmic microwave background. Such a black hole would actually absorb more radiation from the universe than it emits. Hawking radiation is only observable, in principle, for tiny black holes, and it has never been directly detected. But Hawking radiation has enormous theoretical consequences. It tells us that black holes are thermodynamic objects with a temperature and an entropy, and the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is extraordinary. Entropy is normally an extensive quantity, scaling with volume. The fact that black hole entropy scales with area was the first hint of what would become one of the most important ideas in theoretical physics, the holographic principle. The discovery that black holes radiate was wrong in the sense that it contradicted what we thought we knew. Black holes were supposed to be eternal, dark, forever. Hawking showed they are none of these things. They radiate, they cool, they lose mass, and eventually they vanish entirely, leaving behind only the radiation they emitted during their long evaporation. What happens to the information that fell in when the black hole evaporates? This is where the information paradox becomes most acute. Hawking originally argued that the information is simply lost, that the evaporation is thermal radiation carrying no information about what fell in. This would mean quantum mechanics is fundamentally wrong or incomplete. Most physicists today believe Hawking was wrong about this. They believe information must be preserved somehow. But how? That is the question nobody has fully answered yet. The singularity at the centre of a black hole, the point where general relativity predicts density becomes infinite and space-time curvature becomes infinite, is almost certainly wrong. Not wrong in the sense that something unusual and extreme does not happen at the centre of a black hole. Something certainly does. But the prediction of literal infinite density is almost certainly a sign that general relativity is breaking down as a theory, reaching the limits of its validity rather than an accurate description of what actually exists inside a black hole. Every time physics has encountered an infinity in a calculation, it has historically been a sign that the theory producing the infinity is incomplete. The ultraviolet catastrophe in the physics of blackbody radiation, where classical electromagnetism predicted that heated objects should radiate infinite energy at high frequencies, was resolved by quantum mechanics. The infinity at the centre of a black hole is widely believed to be resolved by a theory of quantum gravity, a theory that correctly describes gravity at the quantum scale. We do not have such a theory. We have candidates. String theory, loop quantum gravity, and several other approaches all attempt to provide a consistent quantum theory of gravity. None has yet been confirmed experimentally. None has yet made distinctive testable predictions that distinguish it from its competitors. What these theories generally agree on is that the classical singularity, the point of literally infinite density, does not exist in the final theory. The extreme conditions at the centre of a black hole will be described by quantum gravity, and quantum gravity will replace the classical singularity with something finite, something strange and extreme and far beyond ordinary experience, but not literally infinite. What that something is, we do not know. The interior of a black hole is, in a genuine sense, the most unknown place in physics. Not because we lack clever people thinking about it. Because the physics that would describe it, quantum gravity, does not yet exist in a form we can use to calculate what happens there. This is a remarkable situation. Black holes are among the best studied objects in astrophysics. We have detected gravitational waves from merging black holes. We have imaged the shadow of a black hole. We understand their thermodynamics, their formation, their influence on surrounding matter. And yet the interior of a black hole, the region that general relativity predicts, and that is, in some sense, the defining feature of a black hole, remains genuinely unknown. We thought we knew what was inside a black hole because we had equations that described it. The equations break down. The true interior is a mystery. For most of the 20th century, black holes were thought of as exotic objects, rare products of specific kinds of stellar death, scattered thinly through the galaxy and playing a minor role in the large-scale structure of the universe. This picture was dramatically wrong. We now know that black holes are extraordinarily common. In fact, they come in two vastly different size classes that are both far more prevalent than anyone initially expected. Stellar mass black holes formed from the collapse of massive stars are now estimated to number in the hundreds of millions in the Milky Way alone. Every massive star that has ever lived and died in our galaxy, every star with a mass greater than roughly 20 times that of the Sun, is a potential black hole progenitor. The galaxy has been forming stars for about 10 billion years. Many massive stars have lived and died in that time. The remnants of many of them are stellar mass black holes, scattered through the galaxy, mostly invisible because they are not actively accreting material. The number was shocking when its implications were worked out. Hundreds of millions of black holes in our galaxy alone. In a galaxy of 200 to 400 billion stars, black holes constitute a small but significant population of the compact objects present. They are not rare exotic exceptions to the normal population. They are a standard endpoint of stellar evolution for a specific mass range. But the bigger shock came from the centres of galaxies. In the 1960s and 1970s, the discovery of quasars raised the question of what could possibly power such extraordinarily luminous objects. Quasars are among the brightest objects in the observable universe, outshining entire galaxies of hundreds of billions of stars from a region not much larger than a solar system. The only mechanism capable of producing this much energy from such a small volume is the gravitational potential energy of matter falling onto a supermassive black hole. But the existence of supermassive black holes at the centers of distant active galaxies seemed compatible with the view that such objects were rare, associated only with the dramatic environments of quasars. Most galaxies, including our own Milky Way, did not appear to be quasars. The revelation came gradually over the 1980s and 1990s from careful observations of the centers of nearby galaxies. Astronomers tracked the velocities of stars and gas near galactic centers. The orbital velocities they measured implied the presence of enormous masses concentrated in very small volumes, too small and too massive to be any ordinary collection of stars. Every large galaxy examined, not just quasars, not just unusual galaxies, but ordinary spiral galaxies and elliptical galaxies of various sizes, appeared to harbour a supermassive black hole at its centre. The masses ranged from millions to billions of times the mass of the Sun. Our own Milky Way has one. It is called Sagittarius A. It has a mass of approximately 4 million times the mass of the Sun. For most of the galaxy's history, it has been relatively quiet, not accreting much material. But the evidence for its existence is unambiguous from the precise tracking of stellar orbits near the galactic centre over many years. Black holes are not rare exotic objects. They are a standard feature of the universe. Every massive star becomes one. Every large galaxy contains one at its centre, a behemoth millions or billions of times more massive than the Sun, sleeping quietly or blazing as a quasar, depending on how much material is falling onto it. The universe is full of black holes. We were wrong to think otherwise. When it became clear that every large galaxy contains a supermassive black hole at its centre, the initial picture was that the black hole was a passenger. A massive object sitting at the centre of the galaxy, contained by the galaxy's gravity, feeding occasionally on available gas and stars, but otherwise a bystander in the galaxy's evolution. This was wrong. The relationship between a supermassive black hole and its host galaxy is not that of a passenger and a vehicle. It is something closer to a partnership, or perhaps a mutual regulation, a feedback relationship in which each shapes the other over billions of years. The evidence that something was wrong with the passenger picture came from an unexpected correlation. Astronomers measuring the masses of supermassive black holes in many different galaxies found that the mass of the central black hole is tightly correlated with properties of the galaxy's central bulge, specifically with the velocity dispersion of stars in the bulge, a measure of how fast the stars are moving on average. This correlation, called the M-sigma relation, implies that the black hole and the galaxy's bulge evolved together, their properties linked by some process that regulated the growth of both simultaneously. But the Schwarzschild radius of a supermassive black hole is tiny compared to the galaxy that contains it. The black hole's gravity directly influences only the small region immediately around it. How could something so comparatively small be linked so tightly to the properties of the much larger galaxy? The answer is feedback. When a supermassive black hole is actively accreting material, it can release enormous amounts of energy. Some of this energy is in the form of radiation. Some is in the form of powerful jets, collimated streams of plasma launched along the black hole's spin axis at speeds close to the speed of light. And some is in the form of winds of hot gas driven away from the accreting material by radiation pressure. These jets and winds and radiation can interact with the gas throughout the galaxy, heating it, dispersing it, suppressing the formation of new stars. When the black hole grows large enough and active enough, it can effectively blow away the gas that would otherwise form new stars in the host galaxy, quenching star formation and regulating the galaxy's growth. Conversely, when star formation is high and there is plenty of gas, some of it falls toward the galactic center and feeds the black hole, causing it to grow and become more active. The system self-regulates, with the black hole and the galaxy exchanging energy and matter over billions of years in a feedback loop that determines the final properties of both. Black holes are not passengers in galaxies, they are co-architects. The supermassive black hole at the center of the Milky Way helped shape the galaxy we live in. regulating the rate of star formation, influencing the distribution of gas and dust, participating in the galaxy's evolution over 10 billion years. The story of a galaxy is not separate from the story of its central black hole. They are the same story. When two black holes orbit each other and gradually spiral inward, losing energy and angular momentum, and eventually merge, we thought there was essentially nothing to observe. Black holes, by definition, do not emit light. A merger of two black holes in the pre-2015 view would be a completely dark event, undetectable from Earth. This was spectacularly wrong. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time in history. The signal lasted about 0.2 of a second. It corresponded to the merger of two black holes, one of approximately 36 solar masses and one of approximately 29 solar masses, at a distance of about 1.3 billion light-years from Earth. The merger was not silent. It was, for a fraction of a second, more powerful than the combined luminosity of all the stars in the observable universe. Not in electromagnetic radiation, not in light, but in gravitational waves, ripples in space-time itself propagating outward from the cataclysm at the speed of light. The amount of energy radiated away as gravitational waves during the merger was approximately 3 solar masses converted entirely to energy. Einstein's equation, E equals mc², gives us the magnitude of this. 3 times the mass of our Sun, converted entirely into ripples in the fabric of space-time. In a fraction of a second, the gravitational waves arrived at Earth as a distortion in space-time so small that the LIGO detectors, which measure the relative change in length between perpendicular arms 4 kilometers long, detected a displacement of approximately 1,000th the diameter of a proton. This is among the most precise measurements ever made by human technology. The detection of gravitational waves opened an entirely new way of observing the universe. Electromagnetic astronomy, the observation of light in all its forms from radio waves to gamma rays, had been the primary tool of astronomy for all of human history. Gravitational wave astronomy added a completely new window, capable of detecting events that produce no electromagnetic radiation, including the mergers of black holes. Since the first detection in 2015, LIGO and its partner observatories have detected dozens of black hole mergers and several neutron star mergers. Each detection reveals information about the masses, spins, and distances of the merging objects. The statistical properties of the detected mergers are already telling us about the population of black holes in the universe, their mass distribution, their formation channels. We thought merging black holes were silent and undetectable. They turned out to be the most energetically powerful events in the observable universe, radiating away solar masses of energy in fractions of seconds as ripples in spacetime that we can now detect with instruments on Earth. The defining feature of a black hole is that it does not emit light. By definition, it cannot be directly observed in the way that a star or a galaxy can be observed. This led to the natural assumption that black holes are invisible, that we can only infer their presence from their effects on surrounding matter, never see them directly. In 2019, this assumption was overturned. The Event Horizon Telescope Collaboration, a global network of radio telescopes linked together to function as a single instrument the size of the Earth, released the first direct image of the region around a black hole's event horizon. The target was the supermassive black hole at the centre of the galaxy M87, a giant elliptical galaxy approximately 55 million light-years away. The M87 black hole has a mass of approximately 6.5 billion times the mass of the Sun. Its event horizon has a radius of approximately 20 billion kilometres, so large that it would extend well beyond the orbit of Neptune if placed at the centre of our solar system. The image shows a bright ring of light surrounding a dark central region. The bright ring is the shadow of the photon sphere, the region where photons orbit the black hole on circular paths, illuminated by the hot gas accreting onto the black hole. The dark central region is the black hole's shadow, the area where the black hole's gravity prevents light from reaching the observer. What the image shows is not the black hole itself, because the interior of the event horizon cannot emit light, but it shows the direct effect of the event horizon on the light in its immediate vicinity, the darkening of the sky in the region where the event horizon lies, surrounded by the bright emission of the infalling material. In 2022, the same collaboration released an image of Sagittarius A, the supermassive black hole at the centre of our own Milky Way. This was technically more challenging than the M87 image because Sagittarius A is much smaller, its mass 4 million solar masses versus 6.5 billion, and because the material around it varies on timescales of minutes, requiring sophisticated techniques to combine images taken at different times. We can see black holes, not their interiors, not the singularity, not what lies beyond the event horizon, but the shadow that the event horizon casts on the surrounding universe, the dark circle surrounded by fire that marks the point of no return. The assumption that black holes are invisible was wrong. They are not. They cast shadows, and those shadows are now photographed. The popular image of a black hole is purely destructive, a cosmic vacuum cleaner, a void that sucks in everything around it, the ultimate engine of annihilation. Once something falls in, it is gone. Black holes only take. This picture is incomplete and in important ways misleading. Black holes give back, not what they take, but something. The most dramatic giving back is in the form of jets. Many accreting black holes, both stellar mass and supermassive, produce relativistic jets, collimated streams of plasma and electromagnetic radiation launched along the black hole's spin axis at speeds that are significant fractions of the speed of light. The mechanism that produces these jets involves the interaction of the rapidly spinning black hole with the magnetic fields in the surrounding accretion disk, extracting rotational energy from the black hole and converting it into the kinetic energy of the jet. The jets from supermassive black holes can extend for millions of light years, far beyond the bounds of the host galaxy. They deposit enormous amounts of energy into the intergalactic medium, heating the gas that would otherwise fall back onto galaxies and form new stars. This feedback, as we discussed in the context of galaxy evolution, regulates star formation across entire galaxies and even across clusters of galaxies. The jets from the M87 black hole, one of the first to be studied in detail, extend for approximately 5,000 light-years and are visible in radio waves and X-rays. They are carrying energy extracted from the black hole's rotation out into the universe, heating gas, suppressing star formation, and leaving a lasting imprint on the large-scale structure of the galactic cluster in which M87 sits. Black holes also give back through the material they eject before it falls in. The accretion process is not perfectly efficient at sending material into the black hole. A significant fraction of the infalling material is heated and ejected by radiation pressure and magnetic processes, returning to the interstellar medium with higher energy than it had when it began falling. This recycled material, enriched by the high-energy processes near the black hole, contributes to the chemical enrichment of the galaxy and the universe. And in the very long run, black holes give back through Hawking radiation. Over timescales incomprehensibly longer than the current age of the universe, black holes evaporate, converting all the mass that fell into them into thermal radiation that spreads out into the universe. The mass that formed the black hole eventually, after an almost incomprehensibly long time, returns to the universe as low-energy radiation. Black holes are not purely destructive, they are transformers of energy and matter, taking in material and converting it into jets, winds, radiation, and eventually, over timescales longer than anything we can directly observe, back into radiation that rejoins the universe. We have known for decades that stellar mass black holes form when massive stars exhaust their nuclear fuel and undergo gravitational collapse. The theoretical framework for this process is well developed, grounded in solid physics, and confirmed by observations of supernova explosions and their remnants. But the formation of supermassive black holes remains genuinely mysterious. A supermassive black hole in the centre of a mature galaxy has a mass of millions to billions of times the mass of the Sun. If it grew to this mass by accreting matter at normal rates since the formation of the galaxy, that would take billions of years. For nearby galaxies in the present-day universe, this is enough time. The Milky Way is about 13 billion years old. The black hole at its centre has had time to grow to 4 million solar masses through normal accretion processes over this timescale. But astronomers have discovered quasars with supermassive black holes of billions of solar masses when the universe was less than 1 billion years old. The universe itself has only been around for 13.8 billion years. If these black holes started from stellar mass progenitors and grew by normal accretion, they would need to grow at the maximum possible rate, the Eddington limit, continuously for hundreds of millions of years to reach their observed masses. Even this seems barely possible in the available time, and requires the black holes to start from seeds much more massive than ordinary stellar mass black holes. Where did the seeds come from? How did the first supermassive black holes form so early in the universe's history? Several mechanisms have been proposed. Direct collapse black holes, formed when massive clouds of primordial gas collapse directly into a black hole without first forming a star, could produce seeds of 10,000 to 100,000 solar masses, giving the subsequent growth by accretion a much more favourable starting point. Stellar mass black holes could merge rapidly in dense early star clusters, building up mass more quickly through mergers than through accretion. The remnants of the first generation of massive stars, which were likely much more massive than stars today, could form unusually large black hole seeds. None of these mechanisms has been definitively confirmed. The James Webb Space Telescope, with its ability to observe the most distant and earliest galaxies, is actively searching for the signatures of supermassive black hole formation in the early universe. Early results have found that supermassive black holes in the early universe are even more massive than theoretical models expected, deepening the mystery rather than resolving it. We understand how stellar mass black holes form. We do not fully understand how the universe's largest black holes formed. The formation of the behemoths at the centres of galaxies remains one of the open questions of modern astrophysics. We have mentioned the black hole information paradox several times, the conflict between black hole physics and quantum mechanics over whether information can be destroyed. It is worth spending more time on this, because the physics community's understanding of its importance has itself undergone a major revision. When Hawking first identified the paradox in the 1970s, it was treated by much of the physics community as an interesting technical problem, but perhaps not a fundamental crisis. Maybe quantum mechanics allowed information destruction in extreme circumstances. Maybe the problem would be resolved when quantum gravity was better understood. It was a puzzle, but not necessarily a shattering challenge to the foundations of physics. Over the following decades, the sense of crisis grew. Increasingly, physicists came to believe that information destruction is not a small modification to quantum mechanics. It is a fundamental violation of the mathematical structure of the theory. Quantum mechanics is built on the principle of unitarity, the requirement that the total probability of all possible outcomes of a quantum process always sums to 1. Information destruction violates unitarity, and unitarity is not a minor technical detail. It is central to the consistency of the entire framework. By the 1990s, the information paradox was recognized as a genuine crisis, a contradiction at the intersection of two of the most successful theories in physics, general relativity and quantum mechanics. Then, in 1997, the Argentine physicist Juan Maldacena published a paper that transformed the discussion. Maldacena found a correspondence, now called the ADS/CFT correspondence, between a theory of gravity in a certain type of spacetime and a quantum field theory without gravity on the boundary of that spacetime. The two theories are dual to each other, equivalent descriptions of the same physics. The quantum field theory in Maldaceno's correspondence is manifestly unitary, manifestly information-preserving. If the correspondence holds exactly, then the gravitational theory it is dual to must also be information-preserving. Black holes in the gravitational theory must somehow preserve information, even if we cannot yet see exactly how. Maldaceno's paper is one of the most cited in the history of theoretical physics. It strongly suggested that information is not destroyed in black holes, that Hawking's original conclusion was wrong, and that the resolution of the paradox requires a modification of how we think about the interior of black holes, or the nature of Hawking radiation. But the paradox is not yet resolved. We know the answer must be that information is preserved. We do not fully understand the mechanism. The interior of black holes, the singularity, the final stage of evaporation, all remain inadequately understood. The information paradox is not a minor technical problem. It is a window into the deepest questions about the nature of space-time, information, and quantum gravity. This is perhaps the most radical of the wrong ideas, and it is still very much in the process of being overturned. It may not be completely wrong, but the evidence increasingly suggests it is incomplete. The assumption that space-time is fundamental, that it is the basic arena within which physics occurs, a smooth continuous fabric that exists at all scales and in which all other physics takes place, is being challenged. The challenge comes from several directions, from the black hole information paradox and the holographic principle. We have learned that the amount of information in a region of space is not proportional to its volume, but to the area of its boundary. This is the holographic principle, one of whose implications is that a three-dimensional region of spacetime can be completely described by a two-dimensional theory on its boundary. The three-dimensional interior, in some sense, emerges from the two-dimensional boundary. If the interior is not more fundamental than the boundary, if a region of spacetime is in some sense equivalent to a lower-dimensional theory on its surface, then spacetime may not be the fundamental background that we assumed. It may be an emergent description, arising from some more fundamental structure that does not look like spacetime at the most basic level. From the study of quantum entanglement, another direction leads to the same conclusion. Maldacena and Leonard Susskind proposed a connection between quantum entanglement and the geometry of spacetime, captured in the slogan ER equals EPER, where ER refers to Einstein-Rosen bridges, which are the technical term for wormholes, and EPER refers to Einstein, Podolsky, and Rosen, who first discussed quantum entanglement. The proposal is that entangled particles are connected by tiny wormholes in spacetime, that entanglement and geometry are related, that the geometric structure of spacetime is in some sense built out of quantum entanglement. If this is right, then spacetime is not the fundamental arena. It is built from quantum information. Geometry is an emergent property of the quantum state of the universe, not a background that the quantum state evolves within. These ideas are still highly speculative and vigorously debated. They have not been confirmed experimentally, but they represent the frontier of theoretical physics, the place where the deepest questions about the nature of reality are currently being pursued. And they suggest that the assumption that spacetime is fundamental may be one of the most significant wrong ideas that needs to be overturned as physics advances. In 2012, a paper by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, known by the author's initials as the AMPS paper, sharpened the information paradox into what they called the firewall paradox, a contradiction so stark that it seemed to require choosing which of several fundamental principles of physics to abandon. The argument went roughly as follows. If information is preserved in Hawking radiation, as the ADS-CFT correspondence strongly suggests, then the late Hawking radiation must be entangled with the early Hawking radiation. This is required for the radiation to carry information about what fell in, building up correlations over time as the black hole evaporates. But the equivalence principle of general relativity, the principle that an infalling observer should notice nothing special at the event horizon, requires that the Hawking radiation near the horizon be in a specific quantum state that is entangled with the interior of the black hole, not with the distant early radiation. A quantum particle cannot be maximally entangled with two different things simultaneously. This is a fundamental principle of quantum mechanics called monogamy of entanglement. If the late radiation is entangled with the early radiation for information to be preserved, and also entangled with the interior for the equivalence principle to hold, we have a contradiction. Something must give. Either information is not preserved, violating quantum mechanics, or the equivalence principle fails at the horizon, meaning an infalling observer does not have a smooth crossing, but instead encounters a wall of high-energy radiation at the horizon, a firewall. Or the description of the black hole interior in terms of ordinary spacetime breaks down in some more subtle way. The firewall paradox shook the theoretical physics community. The consensus that had been building since Maldaceni's work, that information is preserved, and the crisis would somehow be resolved, was now confronted with a concrete argument that resolution required sacrificing one of the most fundamental principles of general relativity. Various resolutions have been proposed. Some involve modifications of how we think about the black hole interior. Some involve the ER equals E-per connection between entanglement and geometry. Some involve new physics at the event horizon that is not captured by standard general relativity. None has achieved consensus. The firewall paradox is, as of the present, unresolved. It is one of the most intensely debated problems in theoretical physics. It is a sign that our understanding of black holes, which has been substantially revised over the past century, is not yet complete. Let us return for a moment to the image of M87's black hole released in 2019, because it deserves more attention than we have given it. The Event Horizon Telescope is not a single instrument. It is a network of radio telescopes located at different observatories around the world, coordinated to observe the same target at the same time. By combining their observations, the network achieves an effective resolution equivalent to a radio telescope the size of the Earth, sufficient to resolve the shadow of the M87 black hole at 55 million light-years distance. The observations were made in April 2017. The data collected in those observations filled hard drives that had to be physically flown to a central processing facility, because the amount of data was too large to transmit over the internet in a reasonable time. Petabytes of data, collected at observatories on multiple continents and at the South Pole, all brought together and processed using sophisticated algorithms to produce the final image. The result was the first direct visual evidence of an event horizon, a ring of light, slightly asymmetric because the material on the side moving toward us is Doppler boosted to appear brighter, surrounding a central darkness that is the shadow of the event horizon. The image confirmed several predictions of general relativity for black holes. The size of the shadow is consistent with the prediction for a black hole of 6.5 billion solar masses. The asymmetry of the ring is consistent with the expected Doppler effect for a rotating accretion disk. The sharpness of the boundary between the bright ring and the dark shadow is consistent with the predictions for photon orbit structure near a black hole. General relativity passed the test. The event horizon exists as predicted. The shadow is as large as the equations say it should be. But the image also raised questions. The structure of the emission region, the specific patterns of brightness within the ring, contain information about the accretion physics near the black hole that is not yet fully understood. Subsequent images, taken at later times, show that the structure changes. The bright and dark regions within the ring shift as the turbulent accreting material moves. Understanding these changes requires models of plasma physics in extreme gravitational environments that are actively being developed. The image was a triumph of general relativity and of human ingenuity. It was also the beginning of a new era of direct observation of black holes, one that will yield more images, more detailed observations, and almost certainly more surprises. The gravitational wave detection of September 14, 2015 deserves its own careful attention, because it was not just a confirmation that black holes exist and merge, it was the opening of a new sense. For all of human history, astronomy has been visual. We observe the universe by collecting light, electromagnetic radiation of various frequencies. We have extended this visual sense with instruments far beyond what our eyes can detect, from radio telescopes to gamma-ray observatories, but it has always been about electromagnetic radiation, about photons, about light in its broadest sense. Gravitational waves are not light. They are not electromagnetic radiation. They are ripples in the geometry of space-time itself, propagating outward from accelerating masses at the speed of light, but through a completely different physical channel. They interact with matter so weakly that they pass through the Earth as if it were not there. They are, in a sense, the purest possible signal from the most extreme events in the universe, unscattered, undimmed by anything they pass through. Detecting them required building instruments of extraordinary sensitivity. The LIGO detectors are L-shaped devices with arms 4 kilometers long. At each detector, a laser beam is split and sent down both arms, reflected off mirrors at the ends, and recombined. If a gravitational wave passes through, it compresses space in one direction and stretches it in the perpendicular direction, changing the relative lengths of the two arms by a tiny amount. The change in length that was detected on September 14, 2015, was about 4/1000th of the diameter of a proton. The signal, when converted to sound by mapping the frequencies of the gravitational wave to audible frequencies, is a chirp, a brief rising tone lasting a fraction of a second. The frequency rises as the two black holes spiral closer together, orbiting faster as their separation decreases, until the moment of merger when the frequency jumps and then rapidly decays as the merged black hole rings down to its final state. In that fraction of a second chirp is the story of two black holes that spent perhaps 1 billion years spiraling together, losing energy to gravitational radiation at an imperceptibly slow rate, until in the final moments the radiation became intense and the collision happened quickly, and the merged black hole settled into its final state. We heard it. After 1 billion years of approach, in a fraction of a second, we detected the sound of two black holes becoming one. Since that first detection, gravitational wave astronomy has grown into an active field. Multiple mergers are now detected every few weeks. The catalogue of merging black holes and neutron stars is growing, providing statistical information about the population of compact objects in the universe that no other observation could provide. The universe speaks in gravitational waves. We are now listening. Stephen Hawking is perhaps the most publicly famous physicist of the late 20th century, and his contributions to the understanding of black holes were genuinely revolutionary. But the picture is more nuanced than the public image of Hawking as infallible suggests. Hawking got some things profoundly right and other things profoundly wrong, and the process of working out where he was right and where he was wrong has been one of the driving forces of theoretical physics for the past several decades. What Hawking got right was the discovery of Hawking radiation itself. The argument that black holes radiate thermally due to quantum effects near the event horizon is solidly grounded in the physics of quantum field theory in curved spacetime. The Hawking temperature, proportional to the surface gravity of the black hole divided by fundamental constants, is a well-defined prediction. The connection between black hole thermodynamics with temperature and entropy, and the laws of ordinary thermodynamics was established by Hawking and his collaborators and remains one of the deepest results in theoretical physics. What Hawking got wrong was his conclusion about the fate of information. In 1975 and for several decades subsequently, Hawking argued that information that falls into a black hole is permanently destroyed, that the Hawking radiation carries no information about the infalling matter, that the evaporation of a black hole results in a pure thermal state with no trace of the information that fell in. This conclusion, which Hawking defended strenuously for decades, appears to be wrong. The ADS/CFT correspondence and subsequent developments in theoretical physics have made it increasingly clear that information must be preserved. In 2004, Hawking publicly conceded the argument, announcing at a conference in Dublin that he had been wrong about information loss, and that information is preserved in black hole evaporation. He proposed a specific mechanism involving the path integral over different spacetime topologies. Most physicists considered his 2004 proposal incomplete rather than definitive, and the question of exactly how information is preserved remains open. But Hawking's concession was a significant moment in the history of the information paradox, an acknowledgement by the physicist who had most prominently championed information loss that the argument had been lost. Hawking was also, arguably, wrong in his later years about the firewall paradox. When AMPS published their argument, Hawking's response was to propose that black holes do not have event horizons, replacing them with what he called apparent horizons. This proposal was widely discussed but not widely accepted, and most physicists consider the firewall paradox to require a more nuanced resolution. Hawking's legacy on black holes is complex. He identified the deepest problem in the field, information loss, and was ultimately wrong about the answer to that problem. He discovered Hawking radiation, which turned out to be correct, and which raised the question. He was, in a sense, both the person who created the most important puzzle and the person who got the answer wrong, leaving the resolution for others to find. That is not a criticism. It is a description of how science works at the frontier. After all of these corrections, all of these overturnings of what we thought we knew, what is the picture of black holes that we are left with? It is messier than what we had before, and more interesting. Black holes exist. They are common. They range from stellar mass objects formed by the deaths of massive stars to supermassive behemoths of billions of solar masses at the centres of galaxies. They are not mere endpoints of matter, passive recipients of infalling material. They are active participants in the evolution of galaxies, regulating star formation through jets and winds, co-evolving with the galaxies they inhabit. The event horizon is a global causal boundary, not a local physical surface. An infalling observer does not encounter anything dramatic at the horizon itself for a large enough black hole. What the horizon represents is a point of no causal return, a boundary beyond which information cannot reach the outside universe. But that boundary is at the centre of a profound paradox. Quantum mechanics requires information to be preserved. The semi-classical calculation of Hawking radiation suggests it is not. The resolution of this paradox, which most physicists now believe will ultimately vindicate information preservation, requires physics beyond either general relativity alone or quantum mechanics alone. It requires quantum gravity. The interior of a black hole is unknown in the deepest sense. The classical singularity is almost certainly replaced by something finite, but extreme in the true theory of quantum gravity. What that something is, we do not know. String theory and loop quantum gravity each make proposals, but neither has been confirmed. Space-time itself may not be fundamental. The holographic principle, ER equals EPR, and related developments suggest that geometry may emerge from quantum information, that the smooth continuous space-time of general relativity is an approximation valid at large scales to something fundamentally different at the Planck scale. Black holes are not just astrophysical objects, they are laboratories, theoretical ones, where the deepest questions about the nature of space-time, information, and quantum gravity are most sharply posed. The questions they raise cannot be answered without a theory that unifies quantum mechanics and general relativity, a theory we do not yet have. the picture is incomplete. It is more interesting than what we had before. And the incompleteness is not a failure of science, but a sign that science is working, that the questions are harder than the early answers suggested, and that the universe is stranger than any of our initial models of it. Given how many things we have gotten wrong about black holes, it is worth asking what we might still be getting wrong right now. This is a harder question than it might seem, because the things we are currently getting wrong are, by definition, things we currently believe to be right. We cannot simply look at our current beliefs and identify the errors. If we could, they would already be corrected. But there are regions of genuine uncertainty, places where our current understanding is known to be incomplete or potentially flawed, that suggest where the next revisions might come. The resolution of the information paradox is the most obvious. We believe information is preserved, but we do not know how. The mechanism is unknown, and the answer to this question may require revisions to how we think about the interior of black holes, about the nature of Hawking radiation at late times, about the relationship between entanglement and geometry. The formation of supermassive black holes in the early universe remains mysterious. The James Webb Space Telescope is finding galaxies in the early universe that are more massive and harbour more massive black holes than our models predicted. Something about the early universe allowed black holes to grow faster than our current models account for. What that something is, we do not know. The nature of the singularity inside a black hole is unknown. What quantum gravity does to the classical singularity is genuinely open. String theory makes proposals. Loop quantum gravity makes different proposals. Neither has been tested in any direct way. The answer, when it comes, will almost certainly revise our picture of what is inside a black hole. The fundamental nature of space-time is uncertain in ways we have only recently begun to appreciate. If space-time is emergent from quantum information, if geometry is built from entanglement, then our intuitive picture of a smooth space-time as the arena of physics is an approximation that may break down in ways we have not yet fully mapped. And there may be things we are getting wrong that we have not yet identified, unknowns we have not yet noticed, the things we are wrong about that will be most surprising in retrospect. The history of black holes is a history of surprises. The surprises are not over. There is something important to say about the long list of things we got wrong about black holes. Getting things wrong is not a failure of science. It is how science works. The progression from Michel's dark stars to Schwarzschild's solution to the no-hair theorem to Hawking radiation to the information paradox to the firewall paradox to the event horizon telescope images to gravitational wave astronomy is not a story of errors gradually giving way to truth. It is a story of increasingly precise and increasingly deep engagement with a genuinely difficult and genuinely important set of questions. Each wrong idea was wrong in a productive way. It was wrong in a way that, when corrected, revealed something deeper about the universe than the wrong idea had obscured. The wrong idea that black holes do not exist was corrected by observations that revealed them to be among the most common and most important objects in the universe. The wrong idea that the event horizon is a locally dramatic boundary was corrected in a way that revealed the global causal structure of spacetime. The wrong idea that black holes are cold and dark was corrected by the discovery of Hawking radiation, which opened the door to black hole thermodynamics and the information paradox. The wrong ideas were not wasted time. They were necessary steps. You cannot get to the right answer without first having the wrong answer, examining it carefully, finding where it breaks down, and using the breakdown to triangulate towards something better. This is true of every field of science, but it is particularly clear in the history of black holes, because the story has unfolded so rapidly and the reversals have been so dramatic. In less than a century, we went from physicists doubting that black holes exist to routinely detecting gravitational waves from their mergers, The speed of revision is a sign of healthy science engaging productively with difficult questions. The things we are getting wrong about black holes right now, whatever they are, will similarly be productive errors. The corrections will deepen our understanding in ways we cannot yet anticipate. After all of this, after all the corrections and revisions and open questions, what is a black hole actually? A black hole is a region of space-time from which the escape velocity exceeds the speed of light. This much is essentially as Michel described in 1783, though Michel was using Newtonian physics and the correct framework is general relativity. More precisely, a black hole is a region bounded by an event horizon, a global causal boundary beyond which no causal signal can propagate to the exterior universe. The event horizon is not a physical surface. It is a feature of the causal structure of space-time, defined by what the far future looks like, not by local conditions. Inside the event horizon, in the classical theory, lies a singularity, a region where the equations of general relativity break down. This singularity is almost certainly an artifact of the incompleteness of classical general relativity, replaced in the true theory by something finite but extreme. A black hole has a temperature, the Hawking temperature, arising from quantum effects near the event horizon. It has an entropy, proportional to the area of its event horizon. It will, over a timescale vastly longer than the current age of the universe, evaporate through Hawking radiation. What happens to the information that fell in during the evaporation is not fully understood. Information is almost certainly preserved in some sense, but the mechanism is not yet known. Black holes range in mass from stellar mass objects of a few solar masses to supermassive objects of billions of solar masses. They are formed by the collapse of massive stars and by processes not yet fully understood in the early universe. They are common throughout the universe. They co-evolve with the galaxies that contain them. They produce jets, winds, and radiation that influence star formation across entire galaxies. They can be imaged through the shadow their event horizons cast on surrounding radiation. They can be heard through the gravitational waves produced by their mergers. They are the most extreme objects in the universe, the meeting point of general relativity and quantum mechanics, the place where our current theories most clearly break down, and therefore the place where the next revolution in physics is most likely to come from. In the centre of the Milky Way, approximately 27,000 light-years away, Sagittarius A sits quietly in the dark, 4 million solar masses compressed into a region smaller than the distance from the Earth to the Sun. Around it, stars orbit at extraordinary speeds, their paths betraying the mass at the centre. Occasionally a gas cloud falls closer, and the region brightens briefly, as the infalling material heats and radiates before crossing the horizon. Then quiet again. The event horizon of Sagittarius A is approximately 24 million kilometres across. That is the boundary. On one side, things can escape. On the other side, nothing can. Light that crosses it is gone from our universe forever, or is preserved somehow, encoded in the Hawking radiation that will trickle out over an incomprehensibly long future. We are not sure. Millions of stellar mass black holes drift through the galaxy. Former massive stars, their nuclear fires long extinguished, their matter compressed beyond the density of atomic nuclei, each one a small region of silence in the galaxy's star field. Most of them are invisible, producing no light, revealing themselves only if matter happens to fall onto them and heat up in the process. Somewhere across the universe, two black holes that have been spiraling together for 1 billion years are approaching their final moments. In the next few minutes, or hours, or days, they will merge, and a ripple in space-time will radiate outward at the speed of light. If the geometry is right, if the merger happened at the right distance in the right direction, that ripple will reach our detectors in some months or years, a brief chirp in the data, another entry in the catalogue of mergers. Black holes are happening right now. The universe is full of them. They are shaping galaxies. They are merging. They are evaporating imperceptibly slowly at the Hawking temperature that is barely above absolute zero. They are posing through their existence questions that we do not yet know how to answer. And here you are, on the surface of a planet, under a thin shell of air, inside a galaxy that harbours millions of them, including a supermassive one at its centre, thinking about all of this, letting the strangeness of it settle. The black holes are there whether you think about them or not. The event horizons hold their secrets whether or not we understand them. The information paradox remains open whether or not we have solved it. But you are here, thinking about them, making them, in a specific and local way, known. The universe contemplating its own strangest objects through the medium of a mind on a small planet in the quiet of an ordinary night. That is enough for tonight. Rest now. The black holes will keep their mysteries a while longer. And we will keep asking. Before we move further into what we got wrong, there is a layer of black hole physics that deserves its own careful attention, because it represents one of the most unexpected and profound discoveries in the entire history of physics. Black holes obey the laws of thermodynamics. This statement, which now appears in textbooks as if it were obvious, was completely shocking when it was first proposed. Thermodynamics is the branch of physics that deals with heat, temperature, entropy, and the flow of energy. It was developed in the 19th century to describe steam engines and gases and the behaviour of matter in bulk. It has nothing obvious to do with the geometry of space-time or with objects from which nothing can escape. And yet, in the early 1970s, a young physicist named Jacob Bekenstein, working as a graduate student under John Wheeler at Princeton, noticed something troubling about black holes in the context of thermodynamics. The second law of thermodynamics states that the total entropy of a closed system cannot decrease over time. Entropy is, roughly speaking, a measure of disorder, of the number of ways a system can be arranged while still appearing the same from the outside. Bekenstein noticed that black holes seem to violate the second law. If you drop a hot cup of tea into a black hole, the entropy of the tea, a substantial quantity, vanishes from the observable universe. The black hole, according to the no-hair theorem, is described entirely by its mass, charge, and spin. It has no entropy of its own, or so it seemed. The entropy of the tea is simply gone, and the total entropy of the observable universe has decreased. This cannot be right if the second law of thermodynamics is truly universal. Something must be wrong with the picture. Bekenstein proposed a radical solution. Black holes do have entropy. The entropy of a black hole is proportional to the area of its event horizon. When the tea falls in, the mass of the black hole increases slightly, the event horizon grows slightly, and the entropy associated with the event horizon increases by at least as much as the entropy that was carried by the tea. The second law is saved. Bekenstein's proposal was initially met with skepticism. The idea that a geometric quantity, the area of a surface in spacetime, is equivalent to a thermodynamic quantity, entropy, seemed like a strange and unnatural correspondence. And if black holes have entropy, they must also have temperature. But how can an object from which nothing can escape have a temperature? Temperature requires the emission of thermal radiation, and black holes, by definition, emit nothing. Hawking resolved this apparent contradiction when he discovered that black holes do emit radiation. Hawking radiation gives black holes a genuine temperature. With both temperature and entropy now associated with black holes, the laws of thermodynamics could be extended to include them in a consistent way. The four laws of black hole mechanics, worked out by Hawking, Bardeen and Carter in 1973, are formally identical to the four laws of thermodynamics. The zeroth law of black hole mechanics states that the surface gravity of a stationary black hole is constant over its event horizon, analogous to the zeroth law of thermodynamics, which states that a system in thermal equilibrium has uniform temperature. The first law relates changes in the black hole's mass to changes in its area and angular momentum, analogous to the thermodynamic first law relating changes in energy to heat and work. The second law states that the area of the event horizon cannot decrease, analogous to the thermodynamic second law about entropy. The third law states that the surface gravity cannot be reduced to zero by any physical process, analogous to the impossibility of reaching absolute zero temperature. When these laws were first written down, their authors treated the analogy with thermodynamics as a mathematical curiosity. The correspondence was too perfect to be accidental, but its physical meaning was not yet clear. Hawking's discovery of black hole radiation transformed the analogy into an identity. Black holes are thermodynamic systems. Their surface gravity is their temperature. The area of their event horizon is their entropy. This identity has an implication that reaches far beyond black holes themselves. Entropy is normally an extensive quantity, meaning it scales with the volume of a system. A box of gas twice as large contains twice as much entropy. But the entropy of a black hole scales with the area of its event horizon, not the volume it encloses. This is the origin of the holographic principle, the idea that the information content of a region of space is encoded on its boundary rather than in its interior. The holographic principle, which emerged from thinking about the thermodynamics of black holes, has become one of the central ideas in modern theoretical physics. It suggests that our ordinary three-dimensional description of space may be a kind of projection of a more fundamental two-dimensional description. The three-dimensional interior may be redundant, a way of describing what is more fundamentally encoded on a two-dimensional surface. This is one of the strangest ideas in the history of physics. It has been supported by the ADS-CFT correspondence, which provides a concrete example of a holographic duality. It has influenced how physicists think about quantum gravity, about the nature of space-time, about the relationship between geometry and information, and it all started with a graduate student noticing that dropping a cup of tea into a black hole seemed to violate the second law of thermodynamics. The history of black hole thermodynamics is a story of unexpected connections, of thermodynamic concepts turning up in the geometry of space-time, of entropic reasoning revealing the holographic nature of space. Each step was surprising. Each step turned out to be a window into something deeper. There is a way to extract energy from a black hole, not from inside the event horizon where nothing can escape, but from a region just outside called the ergosphere. This was discovered by Roger Penrose in 1969, and it reveals something profound about the nature of rotating black holes that is deeply counterintuitive. A rotating black hole, described by the Kerr solution to Einstein's field equations, is more complex than a non-rotating Schwarzschild black hole. The rotation of the black hole drags space-time around with it, a phenomenon called frame dragging. Close enough to a rotating black hole, space-time is dragged around so strongly that nothing can remain stationary. Even objects moving in the opposite direction to the black hole's rotation are carried around with it, like leaves in a whirlpool. The region where this happens is called the ergosphere. The ergosphere lies outside the event horizon. Objects can enter the ergosphere and escape back out to infinity. But within the ergosphere, the dragging of space-time has a peculiar consequence. It is possible for particles in the ergosphere to have negative energy, as measured by an observer far from the black hole. Penrose proposed a mechanism that exploits this. An object enters the ergosphere. Inside the ergosphere, it splits into two pieces. One piece falls into the black hole carrying negative energy, which means it reduces the mass and angular momentum of the black hole. The other piece escapes to infinity carrying more energy than the original object brought in. The net result is that energy has been extracted from the black hole. Where does the energy come from? It comes from the rotational energy of the black hole. The Penrose process taps the energy stored in the spin of the black hole, reducing its rotation while extracting energy that can in principle be used. The maximum amount of energy extractable from a rotating black hole through the Penrose process is approximately 29% of the black hole's total mass energy. This is an extraordinary efficiency. The most efficient nuclear reactions convert less than 1% of mass to energy. The Penrose process can, in principle, extract nearly 30%. A related electromagnetic version of the Penrose process, the Blandford-Znajek mechanism, is thought to be responsible for the relativistic jets launched by accreting black holes. The rotating black hole, threaded by magnetic field lines from the surrounding accretion disk, acts as a kind of dynamo, extracting rotational energy and converting it into the kinetic energy of the jet. The jets from M87 and other radio galaxies, extending for thousands or millions of light years, are powered by the spin of the central black hole, tapped by this electromagnetic mechanism. The energy in those jets was once stored in the rotation of the black hole, itself acquired when the black hole formed or grew by accreting angular momentum from infalling material. Billions of years later, that rotational energy is being converted into jets of plasma that heat the intergalactic medium and regulate star formation across an entire galaxy cluster. Black holes are not just sinks, they are batteries. They store energy in their rotation, and that energy can be extracted and deposited back into the universe through jets and through the Penrose process. The black hole eventually loses its spin through this process, becoming a non-rotating Schwarzschild black hole, but not before it has powered some of the most energetic phenomena in the observable universe. Let us pause from the physics for a moment and think about what the numbers actually mean. The supermassive black hole at the centre of M87 has a mass of approximately 6.5 billion solar masses. The Sun has a mass of approximately 2 times 10 to the 30th kilograms. 6.5 billion solar masses is approximately 1.3 times 10 to the 40th kilograms. This is the mass of the black hole. The Schwarzschild radius of this black hole, the radius of its event horizon, is approximately 20 billion kilometers. To put this in perspective, the average distance from the Earth to the Sun is about 150 million kilometers. The event horizon of the M87 black hole has a radius of approximately 130 times the Earth-Sun distance. The orbit of Neptune around the Sun has a radius of about 45 times the Earth-Sun distance. The M87 black hole's event horizon would extend nearly to 3 times the radius of Neptune's orbit. Placed at the centre of our solar system, the M87 black hole's event horizon would engulf Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, and Neptune. All 8 planets of the solar system would be inside the event horizon. The solar system as we know it would cease to exist. And yet, for an observer falling into the M87 black hole, the experience at the event horizon itself would be surprisingly mild. The tidal forces at the event horizon of a black hole this massive are weak. The curvature of space-time at the event horizon, while extreme by ordinary standards, is spread over such a large scale that the difference in gravitational pull between different parts of a human body would be negligible. An observer at the event horizon of M87 would feel nothing unusual. They would not know they had crossed the point of no return. They would simply continue falling into a region from which they could never return, from which no signal they sent could ever reach the outside universe. The inside of the event horizon is genuinely disconnected from our universe in a causal sense. Events inside the event horizon cannot affect anything outside. Information inside cannot reach outside. The observer who has crossed the horizon is still experiencing space-time, still has a future, but that future is entirely contained within the black hole. The singularity, or whatever quantum gravity replaces it with, lies in their future. In the future, because inside the event horizon, the singularity is not in a particular place, it is in a particular time. Space-time inside a black hole is warped in such a way that the singularity is unavoidably in the future of any infalling observer, the way tomorrow is unavoidably in the future of anyone alive today. The observer cannot avoid the singularity by turning in a different direction. any more than you can avoid tomorrow by running in a different direction. Time and space exchange their roles inside a black hole, in a certain formal sense, and the singularity is what lies at the end of the infalling observer's time. This is among the most disorienting features of black hole interiors that general relativity predicts, and it is almost certainly modified by quantum gravity in ways we do not yet understand. The gravitational wave signals detected by LIGO and its partner observatories contain an extraordinary amount of information compressed into a brief chirp of duration less than a second. The inspiral phase, the long period during which two black holes orbit each other and gradually lose energy to gravitational radiation, is not usually detected directly. The energy loss during most of the inspiral is too small to produce signals detectable by current instruments. What LIGO detects is the final few seconds to fractions of a second of the merger, when the two black holes are close enough that the gravitational wave emission becomes intense. During the merger event itself, the two black holes pass through each other and merge. The word merge requires careful interpretation. There are not two event horizons that collide and fuse. Exactly, what happens is that the two regions of space-time from which no escape is possible combine into one region. The event horizon of the merged system forms around both of the original black holes simultaneously, in a process that general relativity describes precisely. In the moment of merger, the combined system is not a black hole. It is a rapidly rotating, highly distorted lump of extreme space-time curvature. This object is called a ring-down. It radiates gravitational waves as it settles into its final, stationary, Kerr black hole configuration. The ring-down signal is a damped oscillation, like the ringing of a struck bell, with a specific frequency and damping rate that depend only on the mass and spin of the final black hole. Reading the ring-down signal can tell us the mass and spin of the final merged black hole with precision. Comparing this to the masses and spins of the two initial black holes tests whether the merger conserved mass energy as general relativity predicts. Every merger detected so far is consistent with general relativity. No deviations have been found. The merger of two black holes of 36 and 29 solar masses, as in the first LIGO detection, produced a final black hole of approximately 62 solar masses. 3 solar masses of energy were radiated as gravitational waves in approximately 0.2 of a second. In that fraction of a second, the power output was approximately 50 times the combined luminosity of all the stars in the observable universe, expressed not in light, but in gravitational waves. The universe has a mode of expression that we discovered only in 2015, after billions of years of these events occurring undetected. How many mergers occurred before we built the instruments to hear them? How many black holes merged while humans were looking at the sky and seeing only silence? The answer is millions, or billions. All of those mergers sent their gravitational wave signals outward through space-time. Many of those signals have already passed the Earth, carrying their information through the planet as if it were not there, undetected, because we did not yet have the instruments. The signals from many more mergers are currently travelling toward us and will arrive in the coming decades as our instruments improve. We are opening our ears to a universe that has been speaking in gravitational waves since the first massive objects formed, and we have only just begun to listen. The holographic principle, which emerged from thinking about the entropy of black holes, has grown into one of the central ideas of modern theoretical physics. It deserves careful attention because its implications extend far beyond black holes and potentially transform how we think about the nature of space itself. The principle was formalized by Gerard Hooft and Leonard Susskind in the early 1990s, building on Bekenstein's observation about black hole entropy. The argument goes as follows. Imagine filling a region of space with as much matter as possible. How much matter can you pack into a given volume before it collapses into a black hole? The answer is that you can pack a maximum amount of mass into a given volume, determined by the requirement that the region not exceed its Schwarzschild radius. This maximum density corresponds to a black hole. Now ask, how much entropy can the matter in this region have? The entropy of a system is bounded by the number of distinguishable states it can be in. The more complex the system, the more states it can have, and the higher its entropy. But we have just established that the maximum density of any region corresponds to a black hole. And the entropy of a black hole is proportional to the area of its event horizon, not the volume it encloses. Therefore, the maximum entropy of any region of space is proportional to the area of the region's boundary, not its volume. This is the holographic bound. The maximum information content of any region of space is determined by the area of its boundary, measured in units of the Planck area, the fundamental length scale of quantum gravity. The implications are profound. In ordinary physics, the amount of information in a region scales with its volume. If you double the size of a box, the information content multiplies by 8. But the holographic bound says the information content scales as the area of the surface, which multiplies by 4 when you double the size. The three-dimensional volume of space appears to be encoding redundant information. All the information in the interior is also encoded on the boundary. This is why the principle is called holographic. A hologram is a two-dimensional surface that encodes a three-dimensional image. The holographic principle says that the universe may be analogously structured, with all the information in a three-dimensional region encoded on a two-dimensional surface surrounding it. Maldaceno's ADS/CFT correspondence provided a concrete mathematical example of this. In his construction, a theory of quantum gravity in a five-dimensional spacetime is exactly equivalent to a quantum field theory on the four-dimensional boundary of that spacetime. The five-dimensional interior is described completely by the four-dimensional boundary theory. Every event in the five-dimensional bulk has a dual description in the four-dimensional boundary, and vice versa. What this means for our universe, which is not the particular kind of spacetime Maldaceno studied, is still being worked out. Extensions of the correspondence to different types of spacetime are active research areas, but the basic idea that our three-dimensional universe might be a holographic projection of information encoded on a two-dimensional boundary has entered the mainstream of theoretical physics as a serious possibility rather than a fringe speculation. If the holographic principle applies to our universe, then the three-dimensional space we inhabit, the space that feels so obviously real and volumetric, may not be the fundamental level of reality. The fundamental description may be two-dimensional, and the three-dimensional world we experience may be an emergent description, correct as an approximation at the scales we inhabit, but not the deepest truth. This is genuinely vertiginous as a claim. It is also, at present, unconfirmed as applied to our actual universe. But it is taken seriously by a significant fraction of the theoretical physics community, and it emerged directly from thinking carefully about what happens to information when matter falls into a black hole. In the Milky Way, scattered through the spiral arms and the halo and the bulge, there are hundreds of millions of stellar mass black holes. Former massive stars, their lives ended in supernova explosions that scattered their outer layers into the surrounding space, while the inner core collapsed beyond neutron star densities into a singularity, or rather, into whatever quantum gravity replaces the singularity with. Most of these black holes are invisible. A black hole in isolation, not accreting any material, emits only Hawking radiation, which for a stellar mass black hole has a temperature far below the temperature of the cosmic microwave background. Such a black hole absorbs more radiation from the universe than it emits. It is cold and dark and detectable only by its gravitational influence on nearby objects. We know they are there. We can calculate how many there should be from the known rate of massive star formation and stellar evolution over the galaxy's history. We can occasionally detect them through gravitational lensing, when a black hole passes between us and a more distant star and its gravity bends the star's light, producing a brightening that follows a specific pattern. We can sometimes detect them when they happen to be in binary systems with normal stars, accreting material from the companion and producing X-ray emission. But for the most part, the stellar mass black holes of the Milky Way are invisible members of the galactic population, drifting through the galaxy on their orbits, slowly being carried around the galactic center over hundreds of millions of years, occasionally passing near enough to a star or gas cloud to accrete some material and briefly shine in X-rays before returning to darkness. They are a substantial component of the mass budget of the galaxy. The total mass in stellar mass black holes in the Milky Way is significant, tens of millions of solar masses at minimum. They influence the dynamics of the galaxy through their gravity. They occasionally merge with each other or with neutron stars, producing gravitational wave events detectable by LIGO. The stellar graveyard is not empty. It is populated by hundreds of millions of dark remnants, the husks of massive stars that burned hot and fast and ended their lives in catastrophic explosions, leaving behind these silent and extreme objects that will persist for longer than any ordinary star, longer than the current age of the universe. Patient in the dark. A black hole evaporates through Hawking radiation. This is almost certainly true, though the mechanism has never been directly observed. The timescale for a stellar mass black hole to evaporate is approximately 10 to the 67th years. The current age of the universe is approximately 14 billion years, roughly 10 to the 10 years. The evaporation timescale is therefore about 10 to the 57th times the current age of the universe. This is not a number that has any intuitive meaning. It is simply vast beyond any comparison to anything in ordinary experience. For a supermassive black hole of 1 billion solar masses, the evaporation timescale is roughly 10 to the 96 years. Even longer, long before any black hole evaporates, the stars will be gone. The last star in the universe, a small red dwarf burning its hydrogen slowly and carefully, will exhaust its fuel in roughly 10 to the 14 years, 100 trillion years from now. After that, the galaxy will contain only white dwarfs slowly cooling, neutron stars, and black holes. The universe will be dark and cold, illuminated only by the faint Hawking radiation from black holes and the even fainter glow of cooling white dwarfs. Over subsequent eons, white dwarfs will slowly cool into black dwarfs, hypothetical objects that do not yet exist, because the universe is not old enough for any white dwarf to have cooled completely. Neutron stars will cool and fade. Galaxies will dissolve as their constituent objects are scattered by gravitational interactions over timescales of tens of trillions of years. The black holes will persist. Long after everything else is dark and cold and dispersed, the black holes will still be there, slowly and imperceptibly radiating away their mass through Hawking radiation. Each one a diminishing presence in an otherwise structureless universe, and eventually each black hole will reach the final stages of its evaporation. As the mass decreases, the Hawking temperature increases, the black hole radiates faster as it gets smaller. In the final moments of evaporation, the process accelerates. The last moments when the black hole is of Planck mass, approximately 22 micrograms, are described by physics we do not yet have. Quantum gravity must be important at these scales. The final burst of evaporation is genuinely unknown. What is left? Hawking radiation, spreading outward, and possibly information, encoded in that radiation in a way that quantum mechanics requires, but that we do not yet understand how to describe. The information that fell in over billions of years of accretion, scrambled and encoded in an extraordinarily complex pattern, released back into the universe in the final evaporation. The black hole is gone. The universe continues, dark and cold, containing only radiation and a few species of fundamental particles at near absolute zero temperature. The era of black holes is over. The long, slow cooling of the universe continues indefinitely. This is what general relativity and quantum mechanics together suggest will happen, in broad outline, over timescales so vast they make the current age of the universe look like a single heartbeat. It is a strange fate for a universe that was once young and hot and full of light. We are living through the golden age of black hole physics. This is not a cliché, it is a precise description of the current moment. In the past decade alone, we have accomplished things that would have seemed like science fiction to physicists of even 30 years ago. We detected gravitational waves from merging black holes for the first time. We imaged the shadow of a black hole's event horizon for the first time. We detected gravitational waves from a neutron star merger and simultaneously observed the electromagnetic counterpart in multiple wavelengths for the first time. We discovered that the early universe contains black holes far more massive than our models predicted. We refined our measurement of Sagittarius A to the point where we could image its shadow directly. Each of these achievements opened new questions. The mass distribution of merging black holes revealed by gravitational wave observations includes pairs in a mass range, between about 50 and 130 solar masses, that stellar evolution models do not easily produce. Where do these intermediate mass black holes come from? The early universe observations from Webb show black holes growing faster than our models allow. How? The theoretical side is equally active. The firewall paradox has sharpened the information paradox into a form that demands resolution rather than deferral. The ER equals EPRA correspondence has suggested deep connections between entanglement and geometry that are still being worked out. Island formula calculations have provided the first explicit calculations of how information might be recovered from an evaporating black hole, using techniques from quantum information theory applied to quantum gravity. These calculations suggest that at late times the Hawking radiation does carry information, but in a form so scrambled that it would be practically impossible to decode. We are in the middle of a revolution in understanding. The revolution is not complete. Many questions are open, many answers are wrong, and we do not yet know which ones. But the pace of progress is extraordinary, and the questions being asked are the deepest that physics can currently pose. You are living during this time. The gravitational waves that were detected in 2015 were the first. Since then, dozens more have been detected. As you read these words, LIGO and its partners are running observation campaigns, detecting mergers, adding entries to the catalogue, building the statistical sample that will tell us about the population of black holes throughout the universe. As you read these words, the Event Horizon Telescope collaboration is processing observations of Sagittarius A and M87 taken in subsequent years, building movies of the changing accretion flow, extracting information about the black hole's spins and the physics of the plasma near the event horizon. As you read these words, the James Webb Space Telescope is observing the most distant galaxies, finding evidence of supermassive black holes in the early universe, challenging our models of how they formed. The experiment is ongoing. The universe is the laboratory. Black holes are the most extreme test objects in it. And we are just beginning to run the tests. In the centre of the galaxy, 27,000 light-years from Earth, Sagittarius A sits in quiet. Not absolute quiet. The region around it is active, dense with stars in tight orbits, threaded by magnetic fields, occasionally brightened by flares when gas falls closer to the event horizon and heats up before crossing. But compared to the blazing activity of the quasars that other galaxies' central black holes produce when they are in their feeding frenzies, Sagittarius A is subdued. It is not currently accreting much material. The region around it is relatively clear. We can watch the stars near Sagittarius A. Astronomers have been tracking the orbits of stars within a fraction of a light-year of the galactic centre for decades. The orbits are precise ellipses, exactly as general relativity predicts for orbits around a central mass. The star called S2, or S02 in some naming conventions, has an orbital period of approximately 16 years. At its closest approach to Sagittarius A, it passes within about 120 astronomical units of the event horizon, moving at approximately 3% of the speed of light. The orbit of S2 has been tracked through multiple complete periods. The observed orbit deviates from a Newtonian prediction in exactly the ways general relativity predicts. The orbit precesses, the ellipse slowly rotating at a rate consistent with the relativistic prediction for the mass of Sagittarius A. Measurements of the gravitational redshift of light from S2 at closest approach match the general relativistic prediction precisely. Sagittarius A is not just a black hole we believe exists based on indirect evidence. It is a black hole whose properties we have measured precisely, whose mass we know to within a few percent, whose event horizon we have imaged, whose surrounding stellar orbits we have tracked through multiple periods. It is the best characterized black hole in the universe, simply because it is the closest to us. And it is sitting there right now, at the center of our galaxy, 27,000 light-years away. If you could look in the direction of the constellation Sagittarius, directly toward the galactic center, on a perfectly clear night with perfect eyes, the galactic center would be invisible behind the dust that fills the plane of the galaxy. But it is there. The dense cluster of stars, the magnetic fields, the occasional flares of the accretion flow, and at the center of it all, 4 million solar masses compressed into a region smaller than the Earth's orbit, surrounded by an event horizon that has existed for billions of years and will exist for billions more. It is close, as cosmic distances go. And it is as alien as anything in the universe. One of the things that gravitational wave astronomy has confirmed is a prediction of general relativity that was not directly tested until 2017. General relativity predicts that gravitational waves travel at the speed of light. This seems natural from the perspective of general relativity, where gravity is a geometric property of space-time and gravitational waves are ripples in that geometry propagating at the characteristic speed of the theory. But it was not directly measured until the merger of two neutron stars on August 17, 2017. The neutron star merger, called GW170817, was different from the black hole mergers because neutron stars are not perfectly dark. When they merge, the collision produces a burst of gamma rays, electromagnetic radiation, in addition to gravitational waves. Both the gravitational waves and the gamma rays were detected on August 17, 2017, with a gamma ray burst arriving approximately 1.7 seconds after the gravitational wave signal. The two signals, one carried by gravitational waves and one carried by electromagnetic radiation, travelled from the same event, approximately 130 million light-years away. The difference in arrival time of 7 seconds over a travel time of 130 million years means the speeds of gravitational waves and light differ by less than about 1 part in 10 to the 15th, effectively the same speed. This result placed enormous constraints on theories that propose that gravitational waves travel at speeds different from light. Many alternative theories of gravity, proposed as modifications to general relativity, predicted such differences. The GW170817 observation ruled out or severely constrained a large class of these alternatives. It also confirmed a fundamental symmetry of general relativity. In the theory, all massless fields propagate at the speed of light. Photons, the particles of light, are massless. Gravitons, the hypothetical particles of gravitational waves, are also predicted to be massless in general relativity. A massless particle travels at the speed of light. The observation confirms that gravitational waves do not have a detectable mass, consistent with gravitons being massless as general relativity requires. The gravitational waves from GW170817 were detected by all three interferometers then operating, LIGO Hanford, LIGO Livingston, and the Virgo detector in Italy. Having three detectors allowed the direction of the source to be triangulated, which is how astronomers knew where to point their electromagnetic telescopes to catch the optical counterpart. In the hours and days following the merger, the optical transient was observed by dozens of telescopes worldwide in ultraviolet, optical, infrared, X-ray, and radio wavelengths. This multi-messenger observation, combining gravitational waves and electromagnetic observations of the same event, opened a new era of astronomy. Black hole mergers produce no electromagnetic counterpart, but neutron-star mergers do, and future improvements in detector sensitivity will allow the detection of fainter and more distant events, giving multi-messenger astronomy an ever broader sample of events to study. The speed of gravity is the speed of light. We know this now not just from theory, but from measurement. There is a quality to thinking about black holes at night that is different from thinking about them in daylight, not because black holes are more present at night. They are always there, always the same, 27,000 light-years to Sagittarius A, 55 million light-years to M87, billions of light-years to the quasars blazing at the centres of distant galaxies. The distance does not change with the time of day. But at night, with the darkness that is the sky's natural state without the sun, the universe feels more present. The darkness is not the absence of something. It is the presence of the vast dark space that constitutes most of the universe, made briefly visible by the removal of the sun's overwhelming light. In that darkness, the black holes are there, invisible in their darkness, present in their gravity, shaping the galaxy that contains us, shaping the large-scale structure of the universe through the jets and winds of the most active among them, recording in their event horizons the information about everything that has ever fallen in, slowly and imperceptibly radiating away their mass through Hawking radiation that is too cold to detect. The darkness you see outside on a clear night is not the darkness of a black hole. It is the darkness of intergalactic space, the empty volume between galaxies, and beyond that, the darkness of the observable universe's edge, where the light from the earliest epochs has been stretched into invisibility by cosmic expansion. But the darkness shares something with the event horizon. It is the darkness of things we cannot directly see, whose presence we infer from indirect evidence, whose nature we are still working to understand. Science has given us the ability to look into that darkness with instruments that extend our senses far beyond what evolution provided. With radio telescopes, we see the jets from black holes. With X-ray observatories, we see the hot gas of accretion. With gravitational wave detectors, we hear the mergers. With the Event Horizon Telescope, we see the shadow of the event horizon directly. Each instrument opened a new window. Each window revealed something that was there all along, invisible only because we lacked the means to see it. The universe has always contained black holes. It has always been shaped by them. We simply did not know it until recently. What else is there in the darkness that we cannot yet see? The question is not rhetorical. There are almost certainly things out there that we have not yet found the instruments to detect, phenomena that will seem obvious in retrospect once we develop the means to observe them. Dark matter, whatever it is, fills the galaxy and the universe. Dark energy, whatever it is, drives the expansion. Gravitational waves at frequencies below LIGO's sensitivity band, produced by supermassive black hole binaries orbiting each other over timescales of years, are just beginning to be detected by pulsar timing arrays. The darkness is full. We are only beginning to find what is in it. Behind all of the physics we have discussed, there is mathematics. Equations, specifically, the equations of general relativity, which Einstein published in 1915, and which have proven to be accurate descriptions of gravity at every scale and in every environment where they have been tested. The Einstein field equations relate the geometry of spacetime, encoded in a mathematical object called the Einstein tensor, to the distribution of matter and energy, encoded in the stress-energy tensor. The equations say that matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. These equations are extraordinarily difficult to solve in general. They are a set of 10 coupled nonlinear partial differential equations. Finding exact solutions requires very specific symmetry assumptions. The Schwarzschild solution, valid for a perfectly spherical non-rotating mass in vacuum, was found within months of the equation's publication. The Kerr solution, valid for a rotating black hole in vacuum, was not found until 1963, nearly 50 years later, but the solutions, once found, have proven to be extraordinarily accurate. Every test of general relativity, from the precession of Mercury's orbit to the bending of light around the Sun, to the timing of binary pulsars, to the detection of gravitational waves, to the imaging of black hole shadows, has confirmed the theory to extraordinary precision. General relativity is the most precisely tested theory in all of physics, and yet we know it is incomplete. It predicts singularities which are almost certainly artifacts of its incompleteness. It is incompatible with quantum mechanics at the Planck scale. It does not account for dark matter or dark energy in any fundamental way. It breaks down precisely where black holes take their most extreme forms, at the singularity. The equations that describe the impossible, that describe the curvature of spacetime around a black hole, are correct in every region where they can be tested and break down exactly where we most need them, at the singularity, at the Planck scale, at the intersection with quantum mechanics. This is a precise description of where the next revolution in physics must come from. General relativity is correct as an approximation. It is not the final theory. The final theory, quantum gravity, will contain general relativity as a limiting case and will go beyond it in ways that resolve the singularity, preserve information, and explain what happens at the ultimate endpoints of black hole evaporation. We are waiting for that theory. We have been waiting for a century. The mathematics needed to describe the truly extreme interior of a black hole has not yet been written. The black hole at the centre of our galaxy has a mass of approximately 4 million solar masses. This number is worth sitting with. The Sun is itself extraordinarily massive by any ordinary standard. It contains approximately 9 times 10 to the 30th kilograms. This is about 330,000 times the mass of the Earth. If you took the Earth and multiplied it by 330,000, you would have the Sun. 4 million times that. 4 million times the mass of the Sun, compressed into a region of space with a radius of approximately 12 million kilometers. The radius of the Sun is about 700,000 kilometers. The event horizon of Sagittarius A is about 12 million kilometers in radius, approximately 17 times the radius of the Sun. So the event horizon of Sagittarius A is about 17 solar radii across. This is smaller than many stars. The red supergent star Betelgeuse, which marks the left shoulder of the constellation Orion, has a radius of approximately 800 to 1000 solar radii. The event horizon of Sagittarius A would fit comfortably inside Betelgeuse with room to spare. And yet Sagittarius A contains 4 million times the mass of the Sun, concentrated within that relatively modest volume. The average density within the event horizon is the total mass divided by the volume enclosed by the horizon. For a black hole of 4 million solar masses, this works out to roughly a few kilograms per cubic meter, less dense than water, less dense than air at sea level. This seems paradoxical. How can something be a black hole, a region of extreme gravity, while having a density comparable to a thin gas? The answer is that the event horizon is not a physical surface enclosing dense matter. The matter of the black hole is concentrated at the singularity, which in the classical theory occupies a single point of literally infinite density. The event horizon is a geometric boundary in spacetime, not a physical surface. The average density within the horizon depends on how large the horizon is, and for a supermassive black hole with a very large horizon, this average can be quite low. The extreme gravity is not about average density. It is about the total mass enclosed and the radius at which you are experiencing that gravity. 4 million solar masses, whether compressed to a singularity or spread throughout the horizon volume, produces the same gravitational field outside the horizon. This is one of the counterintuitive features of black hole physics. The extreme gravity is not because the density is extreme at your location if you are outside the horizon. It is because the total mass is large and you are close enough to it that the curvature of space-time becomes significant. 4 million suns, 27,000 light-years away. Right now, quietly sitting at the centre of our galaxy, bending the orbits of stars that pass near it, occasionally brightening when gas falls in, otherwise dark and patient and ancient. There is a thought experiment about black holes that reveals something deeply strange about the relationship between different observers. Consider an astronaut falling into a black hole. From the astronaut's perspective, in their own local reference frame, the experience at the event horizon is uneventful for a large enough black hole. The equivalence principle guarantees this. The astronaut falls through the horizon without noticing anything special. After crossing the horizon, the astronaut continues falling toward the singularity. They can see the outside universe, because light from outside can still reach them after crossing. But they cannot send signals back out. They are inside the event horizon. Their future inevitably ends at the singularity. Now consider an observer far outside the black hole, watching the astronaut fall in. From the outside observer's perspective, something very different happens. As the astronaut falls toward the event horizon, the light they emit takes longer and longer to reach the outside observer, because the light must climb out of an ever deeper gravitational well. The astronaut appears to slow down, never quite reaching the horizon. The light from the astronaut is also increasingly redshifted, its wavelength stretched by the gravitational field. From the outside observer's perspective, the astronaut never crosses the horizon. The astronaut appears to freeze at the horizon, their image growing increasingly redshifted and dim, but never quite disappearing. After a very long time, the outside observer sees the black hole evaporate through Hawking radiation. The information about the astronaut eventually comes back out encoded in the Hawking radiation. So which is it? Does the astronaut cross the horizon and fall to the singularity, or does the astronaut freeze at the horizon and eventually be released in Hawking radiation? Both, neither the answer depends on the observer, and both descriptions are simultaneously consistent with the physics. This is not a contradiction. It is complementarity, a concept from quantum mechanics applied to the gravitational context by Susskind, 't Hooft and others. The outside observer and the infalling observer each have a consistent description of events, but those descriptions are not simultaneously accessible to any single observer. The astronaut's experience of falling through the horizon is not accessible to the outside observer, and vice versa. There is no contradiction, because no single observer can see both descriptions at once. This black hole complementarity principle suggests that the horizon is not simply a geometric boundary in spacetime. It is a boundary of a more profound kind, a boundary where the complementarity of quantum mechanics becomes relevant to the geometry of spacetime. The interior of the black hole as seen by the infalling observer, and the exterior as seen by the outside observer, are not simply two perspectives on the same underlying reality. They are complementary descriptions that are both valid and not simultaneously accessible. This is deeply strange. It suggests that the concept of a single objective spacetime, one that all observers can in principle access, may break down at the event horizon. General relativity assumes a single objective spacetime. Quantum mechanics, applied to the horizon, suggests this assumption may fail. This is another place where general relativity and quantum mechanics come into tension, and where the resolution requires physics beyond both. We have spent a great deal of time on the extreme and the exotic, the singularity, the information paradox, the firewall, the holographic principle. These are the frontier questions, the places where physics is incomplete and potentially wrong. But it is worth stepping back and appreciating black holes as astrophysical objects, embedded in the universe, playing specific and understandable roles in the cosmos. Supermassive black holes at the centres of galaxies are, in their quiescent state, gentle monsters. They sit at the centres of galaxies, their gravity influencing the orbits of stars within a few light years, their presence felt through the M-sigma relation across the galaxy's entire bulge, but mostly quiet, mostly dark. Occasionally flaring as a gas cloud falls in, but not currently doing the dramatic things that quasars do. Quasars are supermassive black holes in their active state, consuming material at high rates, converting the gravitational potential energy of infalling matter into radiation with efficiencies of up to 40%, far exceeding the roughly 1% efficiency of nuclear fusion. The most luminous quasars outshine entire galaxies by factors of hundreds or thousands. They are powered by nothing more exotic than gravity, the most familiar force in the universe, operating under extreme conditions. Stellar mass black holes in binary systems, X-ray binaries, are similarly understandable astrophysical objects. Material flows from the companion star onto the black hole, forming an accretion disk, heating up and radiating X-rays. The X-ray luminosity varies with the accretion rate. The spectrum of the X-rays contains information about the geometry of the inner accretion disk and the spin of the black hole. These are interesting and extreme environments, but they are environments we can model and understand with known physics. The extreme questions about black holes, the information paradox, the nature of the singularity, arise when we try to understand what happens at the event horizon and inside it, at the level of individual quanta rather than at the level of bulk matter and radiation. These are the questions that require new physics. The astrophysics, the behaviour of matter in the region outside the horizon, is in large part understood using the existing frameworks of general relativity, plasma physics, and radiation theory. Black holes are extraordinary. They are genuinely extreme. But they are also, in many respects, ordinary astrophysical objects, following predictable patterns, embedded in the universe as participants in its evolution, susceptible to the same observational and theoretical tools that astronomers apply to other objects. The gentle monster sits at the centre of the Milky Way. It has sat there for billions of years. It will sit there for billions more. And in its sitting, in its patient presence at the centre of the galactic dance, it has helped make the galaxy what it is. Albert Einstein died in 1955. He never knew that black holes are real in the sense of confirmed astronomical objects. He doubted they could exist in nature. He did not live to see the astronomical discoveries of the 1960s and 1970s that confirmed their existence, did not live to see the imaging of quasars and X-ray binaries, did not live to see the tracking of stellar orbits around Sagittarius A, did not live to see gravitational wave astronomy or the Event Horizon Telescope. What would Einstein think of all of this? He would almost certainly be amazed that his equations, which he found so difficult, and which he expected to be practically unsolvable, have proven so accurate in describing these extreme objects. Every test of general relativity that has been performed with black holes, the gravitational redshift of light near them, the precision of stellar orbits, the gravitational wave signals from mergers, the size and shape of the event horizon shadow, has confirmed his theory. In the century since he published the field equations, general relativity has not been found to be wrong in any tested regime. Einstein famously distrusted quantum mechanics and spent the last decades of his life trying to find a unified field theory that would, in his view, transcend both quantum mechanics and general relativity and reveal a deeper deterministic reality. He failed. The unified theory does not yet exist. But the deepest questions in black hole physics today are precisely the questions at the intersection of general relativity and quantum mechanics. the information paradox, the nature of the singularity, the holographic principle, the ER equals EPRA correspondence. These are the questions that require the unification that Einstein sought. Einstein was wrong that quantum mechanics could be replaced or superseded by a deterministic theory. But he was right that there is something deeper to be found at the intersection of gravity and quantum mechanics, something that current physics does not yet fully describe. The questions about black holes are pointing toward that something. He might appreciate the irony. The objects he doubted could exist turned out to be the objects that most sharply point toward the theory he was looking for, the theory that unifies gravity with the quantum, that resolves the singularity, that explains what happens to information in a black hole. That theory is still to be found. Einstein is not here to find it, but he pointed, more accurately than he knew, in the direction from which it will come. The history of our understanding of black holes spans more than 2 centuries, from Michel's dark stars in 1783 to the most recent gravitational wave detections. That is not a long time in the history of human civilization, which stretches back tens of thousands of years. It is a very short time in the history of the universe. In those 2 centuries, the picture has changed dramatically, multiple times. Objects that were doubted to exist turned out to be among the most common in the universe. Objects thought to be eternal turned out to evaporate. Objects thought to destroy information turned out to preserve it. Objects thought to be simple turned out to be the source of the deepest open questions in physics. Objects thought to be silent turned out to be the most powerful sound sources in the universe. Each revision required the patience of scientists who were willing to follow the evidence and the mathematics, even when the conclusions were counterintuitive or uncomfortable. Bekenstein's proposal that black holes have entropy was initially met with resistance because it seemed to violate the principle that black holes have no hair. Hawking's radiation was initially met with skepticism because black holes were supposed to emit nothing. The information paradox was initially treated as a minor technical problem and gradually recognized as a fundamental crisis. Science is not fast, it is not comfortable. It does not produce clean, final answers on schedule. It produces successive approximations to the truth, each better than the last, each revealing deeper questions than it resolves. The black hole information paradox has been open for 50 years. The quantum gravity description of the singularity remains unknown after a century. The formation mechanism of supermassive black holes in the early universe is unknown despite decades of effort. These are not failures. They are signs that the questions are genuinely hard, that they require new ideas, that the next generation of physicists will have important work to do. The patience of science is one of its most important qualities. It does not give up on hard questions. It returns to them, with new tools and new ideas, year after year, until the answer emerges. The answers to the deep questions about black holes will come, not all at once, not soon, but they will come, because the questions are real and the tools are improving, and the community of scientists working on them is persistent. That is the long patience of science, and it is, in its own way, as remarkable as anything it has discovered. Black holes accrete, jets extend, gravitational waves propagate. Somewhere 2 black holes that have been spiraling toward each other for 1 billion years approach the moment of merger. Somewhere a massive star that has exhausted its nuclear fuel is in the final moments before its core collapses, forming a new black hole in a burst of light and neutrinos. Somewhere, Hawking radiation is ticking off the last few quanta of a very small and very old black hole. The final remnant of an ancient stellar death, releasing its last energy into the cold, dark universe. And here, on this planet, in this night, you are resting. The scale of what is happening out there is incomprehensible in the way that the deepest truths often are, too large to hold all at once, too strange to domesticate into ordinary feeling. But it is real. All of it is real. The mathematics describes it accurately. The instruments have detected it. The images have revealed it. The gravitational wave chirps have transmitted it. We got a lot of things wrong about black holes. We thought they were theoretical curiosities. We thought they were rare. We thought they were simple. We thought they destroyed information. We thought we knew what was inside them. We thought merging black holes were silent. We thought we could never see one. We were wrong about all of these things, and being wrong about them led us, through the specific mechanism of science, to a richer and stranger and more accurate picture than any of the wrong ideas contained. The picture is still incomplete. There are things we are currently getting wrong that we have not yet identified. There are questions the answers to which will require physics that does not yet exist. The story is not finished. But what has been discovered is extraordinary, and the process of discovery, the long patient accumulation of observations and calculations and wrong ideas and corrections and sudden insights, is one of the most remarkable things that has happened on this planet in the entire history of life here. We looked at the darkness and found the most extreme objects in the universe. We listened to space-time and heard the mergers. We measured the orbits of stars and found 4 million suns compressed into a space smaller than some stars. We imaged the shadow of the point of no return. We got it wrong, and then we got it more right, and then we got it wrong again in new ways, and then we got it more right again. That is what it looks like to be a civilization in the process of understanding the universe. There is a sense in which black holes cast a shadow larger than themselves. Not literally. The shadow of a black hole, in the technical sense used by the Event Horizon Telescope, is a specific photometric feature around the event horizon, the dark circle where the horizon prevents light from reaching the observer. This shadow is large, larger than the horizon itself because of gravitational lensing, but it is still a finite, measurable thing. But metaphorically, the shadow of black holes extends across the entire history and future of physics. They led us to general relativity's most extreme predictions. They forced the confrontation between general relativity and quantum mechanics that remains unresolved. They produced the no-hair theorem and the information paradox. They produced Hawking radiation and black hole thermodynamics. They produced the holographic principle and the AD-S-CF correspondence. They produced gravitational wave astronomy. They produced the Event Horizon Telescope. They are producing, right now, the most intense theoretical work on the nature of space-time and information and quantum gravity that has ever been done. Everything we have learned about black holes has taught us something beyond black holes. About the nature of space-time, about the nature of information, about the relationship between entropy and area, about the limits of our theories and the directions in which new theories must go. The shadow on the universe that black holes cast is the shadow of questions we cannot yet answer, questions that will drive physics forward for decades or centuries more. The singularity awaits a theory of quantum gravity. The information paradox awaits a full understanding of how Hawking radiation encodes information. The formation of supermassive black holes awaits a better understanding of the early universe. The firewall paradox awaits a resolution that respects both quantum mechanics and the equivalence principle. These are the shadows. And in the long tradition of science, shadows are not obstacles. They are maps. They mark the places where the light of current understanding does not reach, and therefore the directions in which understanding must grow. We are living inside those shadows right now, working at their edges, pushing into the darkness with mathematics and instruments and ideas that do not yet fully exist. The black holes are patient. The questions are patient. And physics, in its long and patient way, is working toward the answers. You have spent time tonight inside the story of black holes, inside the history of what we got wrong, and the ongoing project of getting it more right. But you are also, right now, resting inside a universe that contains black holes, contains hundreds of millions of them in this galaxy alone, contains one at the centre of this galaxy. 27,000 light-years in the direction of Sagittarius. 4 million solar masses sitting quietly in the dark, having been there for most of the galaxy's history and planning to be there long after the Sun has become a white dwarf. You are inside a universe where the expansion of space is carrying distant galaxies away, where the cosmic microwave background fills all of space with ancient radiation, where gravitational waves from black hole mergers pass through the Earth regularly, barely detectable even with the most sensitive instruments we have built, carrying news of cataclysms a billion light-years away. You are inside this universe. You are made of atoms that were forged in stars. You are breathing an atmosphere produced by billions of years of biological activity on a planet that orbits a star that was itself born in the remnants of earlier stellar generations. You are sustained by the energy flowing from a fusion reactor 93 million miles away. You are held to the surface of your planet by the curvature of space-time produced by the planet's mass. Black holes are not separate from this. They are part of the same universe. They formed the same way the Sun formed, from collapsing material. They obeyed the same physics that governs the atoms in your body. They are embedded in the same cosmos that contains everything you are and everything you know. The extreme and the ordinary are not different universes. They are different parts of the same one. The physics that keeps your feet on the ground is the same physics, extended to more extreme conditions, that describes the event horizon of Sagittarius A. The quantum mechanics that governs the chemistry in your cells is the same quantum mechanics that combined with general relativity produces the information paradox. Everything is connected, in the most literal sense, by the laws of physics that govern all of it. We have been through a long journey tonight. Through what we got wrong, why we got it wrong, what we discovered instead. Through the thermodynamics and the information paradox, the jets and the mergers, the imaging and the gravitational waves. Let us name clearly the questions that remain open, the places where the story is unfinished. How is information preserved in black hole evaporation? We believe it is. We do not know the mechanism. The final theory will need to explain precisely how the information that fell into a black hole over billions of years is encoded in the Hawking radiation that comes out over trillions of years. What is inside a black hole? The classical singularity is wrong. Quantum gravity replaces it with something. What? Loop quantum gravity suggests a quantum bounce, where the collapsing matter reaches a maximum density and then rebounds, potentially producing a new region of spacetime. String theory has different suggestions. Neither is confirmed. How did supermassive black holes form in the early universe? The James Webb Space Telescope is finding them more massive and more numerous than models predicted. Something about early universe physics allowed them to grow faster than our current understanding allows. What? Is space-time emergent? Does geometry arise from quantum entanglement? Is the ER equals EPRA correspondence exactly right? And if so, what does it imply about the structure of space-time and the interior of black holes? What is the resolution of the firewall paradox? Does the equivalence principle fail at the horizon? If so, how and what detects the violation? Or is there a more subtle resolution that preserves both information and the equivalence principle? What produces the specific mass distribution of merging black holes observed by gravitational wave observatories? Why are there black holes in the mass gap between 30 and 130 solar masses, where stellar evolution models predict few or no black holes should form? These are the open questions. The frontier. The places where the next generation of physicists will make their names, develop new ideas, run new calculations, make new observations, and hopefully move us closer to the truth. The story of black holes is not finished. It has barely begun, in the sense that the deepest questions it raises are still unanswered. What has been discovered is extraordinary. what remains to be discovered is more so. Science can tell you about black holes. It can tell you about their mass and spin and temperature. It can tell you about the event horizon and the accretion disk and the jets. It can tell you about the gravitational waves from their mergers and the shadow they cast on surrounding light. It can tell you what we got wrong and what we got more right, and what we still do not know. What science cannot give you is what you do with all of this, what it means to you, how it fits into your understanding of what you are and where you are and why any of it matters. Those questions are yours. They always have been. Science provides the material. You provide the meaning. For some people, learning about black holes produces a kind of vertigo, a sense of the scales involved being too large to accommodate, the extremity of the physics too far from ordinary experience to feel real. The information paradox, the holographic principle, space-time being emergent from quantum entanglement, these ideas are deeply strange, and the strangeness can feel like distance, like the universe is too alien to be relevant. For others, learning about black holes produces the opposite, a sense of connection. The realization that the physics governing the extreme environment near an event horizon is the same physics that governs the atoms in your body, that the gravitational waves from a billion-year-old merger pass through your body right now, that the black hole at the center of the galaxy has been shaping the galaxy in which you live for 10 billion years, that you are not separate from all of this, but made of it, embedded in it, a local and temporary expression of the same universe that contains event horizons and Hawking radiation and the information paradox. Both responses are honest. Both are valid. The universe does not require you to feel a particular way about its more extreme features. But the extremity is real. The black holes are there. The questions are open. The universe is stranger and richer and more interesting than any of the wrong ideas that came before. And you are part of it. In the end, a black hole is an answer to a question that nature poses to itself. What happens when you compress matter beyond every possible stopping point? What happens when you exceed not just the limits of electron degeneracy pressure and neutron degeneracy pressure, but every form of pressure that physics provides? What is left when nothing can resist the collapse? A black hole is the answer. A region of space-time from which no information escapes, a point where the laws of physics as we know them reach their limit. A question posed in the form of an object. And in trying to answer what a black hole actually is at the most fundamental level, in trying to understand what happens inside it and what happens to information and what quantum gravity does to the singularity, physics is discovering that the universe is stranger than any of its initial answers suggested. Space-time may be emergent, information may be holographic. The interior and exterior of a black hole may be complementary descriptions that cannot be simultaneously accessed. The singularity may be a quantum bounce to another spacetime. The Hawking radiation may encode everything that ever fell in a pattern so complex that no practical algorithm could decode it, but that preserves, in principle, every bit of information. These are not final answers. They are the current best guesses at the frontier of knowledge. They will be revised. They may be wrong in ways we cannot yet see. But they are the product of a century of thinking carefully about the most extreme objects in the universe, following the mathematics where it leads, testing the predictions against observation, and being willing to revise the picture when the observations demand it. Black holes are wrong about everything we thought they were, and in being wrong, in forcing us to revise everything we thought we knew, they have taken us deeper into the nature of reality than we might have gone otherwise. The event horizon is a boundary, but it is not the boundary of our knowledge. It is a challenge to that knowledge, a place where our understanding runs out and new understanding must be built. Tonight, the black holes are there. The questions are open. The universe is patient. And physics, in its long and patient way, is working toward answers. Rest now. The black holes will keep their secrets a while longer. But not forever. What we knew about black holes was wrong. Almost everything. They do not exist, we thought. They are simple. They are cold and dark. They destroy information. They are silent when they merge. We cannot see them. They are rare. They are separate from the galaxies that contain them. Wrong, 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 wrong. They are common. They are thermodynamic. They evaporate. They preserve information somehow. They produce the most powerful gravitational wave signals in the universe. They cast shadows we can photograph. They co-evolve with galaxies over billions of years. And the singularity at their centres is almost certainly wrong too, replaced by something that quantum gravity will eventually describe and that we do not yet understand. What we got wrong led us to what we got more right. What we get wrong now will lead to what we get more right next. That is the process. It is not efficient, it is not comfortable, but it works. The universe is there, the black holes are there, the questions are there, and the long, patient, magnificent project of understanding continues. Good night. The event horizon holds its secrets. For now, Science for Sleep explores the universe one quiet night at a time. Thank you for spending this night inside one of the deepest mysteries in physics.